Is it working? Oh yes, now I can hear it. Okay. So you fix a time of observation t, a precision epsilon, and you look at the number of distinct orbits that you can observe at this precision during period t. Okay. And then you let t goes to infinity, and you look at the number of distinct orbits you see. And typically, this number of orbits grows exponentially fast with t. So you look at the exponential growth rate, which is the supremum limit of log of number of orbits divided by t. So you take this limit, and then you let the precision be arbitrarily nice, so you let the scale epsilon goes to 0. Okay. And this is the number you get is a topological entropy. And usually it's very hard to compute, but in the setting of holomorphic transformations of compact Kähler manifolds, so compact complex manifold with a Kähler structure, in fact, we can compute it by looking at the action on the cohomology of the manifold. So I will state it for smooth complex projective varieties. Okay, so now X is an algebraic object. It's a smooth complex projective variety. So it's a subset of some projective space, complex projective space defined by polynomial equations, homogeneous polynomial equations. And I will look at holomorphic diffeomorphisms, which in this context are called automorphisms, because all of them, in fact, are defined by algebraic formulas. Oh, yes, it works. Okay, so this means that if the graph of such a holomorphic diffeomorphism in X times X, correct submanifold of X times X. Okay, so you start with such a holomorphic diffeomorphism, and you look at the action on cohomology, and you compute the spectral radius of the define a sequence of them. So for each codimension P, you can look at the action of X star on the HPP of X. So what we do is part of the cohomology of the Hodge decomposition. HPP is the global cohomology. I will come back to that. So we have T numbers where P is dimensional. The maximum. Okay, and then the theorem, the wonderful theorem, says that the true solution of topological entropy finds dynamical is in fact the log of the spectral rate. So there is a lower bound always satisfied. And I said always satisfied for every CVP good transformation. So and there is another one, clearly, related to the Kähler survey. So in our context, we have equality. And this type of numbers, what are or more precisely the long-term T of are the numbers of so here is an example. You start with and say the surface X is this two-dimensional projective given by a polynomial equation. So x, y, and z are affine coordinates on each of the P1. And yes, sorry. So you take, so x is the first coordinate, y the second coordinate, z is the third coordinate. And I just use affine coordinates instead of homogeneous coordinates. And you write such an equation which has the properties that if you fix two of the coordinates, for instance, x and z, and you look at the equation with respect to y, you see a degree 2 equation. This means that if you project x onto P1 times P1, forgetting the y coordinate, okay, you get a 2-to-1 ramified cover. And when you have a 2-to-1 cover, there is a natural involution which permutes the points in the fiber of this 2-to-1 cover. But you can do this in 3 ways. So you have 3 involutions, and you can compose the 3 involutions. And you get a holomorphic diffeomorphism of your complex surface. And if the equation is given by, here I choose rational numbers. So in particular, the coefficients are real numbers. So you can plot the real surface. So you see the shape. And the points here are orbits of this map, this composition of the 3 involutions, several orbits. So you see in the middle here, in fact, there are orbits which seem to be dense. On the top and the bottom, you see some kind of KM behavior with islands and things like that. So you get complicated dynamical systems. And what I just want to look at is the action of this type of transformation on the cohomology. And in that case, the computation is quite simple. The number you get, the most important one, will be lambda 1 in this case, and it's just a quadratic integral. It's 9 plus 4 square root of 5. Okay. So this is the type of transformations I want to look at, but just looking at action on cohomology. Okay, so let me say it again. These numbers, lambda p of f, that we call dynamical degrees, I define them first by talking about spectral radius on cohomology. Here is another way to define them. You can fix a Keller form on X, or what I prefer, you can fix a hyperplane section of X. So X is contained in the projective space, and you can cut X by a hyperplane in your projective space. This is what I call a hyperplane section. And the lambda p of f, here it is, look at the second line. You can compute it like that. So you cut x p times with hyperplanes. So you get a codimension p subset, algebraic subset. You pull it back n times by f. So you get a codimension p subset, which is given by the dynamics of f. You iterate n times. And you want to compute the degree of this algebraic subset of x. So you intersect with other hyperplane sections, and the number of them is the codimension of this. So this is the type of intersection that you need to do to compute the dynamical degree. In fact, then you have to take the nth root and you take the limit. Okay. Or you can do exactly the same computation with scalar forms. Okay, so this explains the name dynamical degree, but because let's look at lambda 1, codimension 1. You take a hyperplane section, so you get a hypersurface in X. You pull it back n times by f, so you get some hypersurface in X. And you want to compute the degree of this hypersurface. Okay, so this is why this is called dynamical degree. So to do that, you intersect with a new hyperplane section the right number of times, and you take the nth root at the limit. Okay, so that's the kind of number we are interested in. In fact, in the rest of the talk, I will focus on lambda 1. And you see this definition here, I mean, you just have to define this intersection product. And this can be done in algebraic geometry. So I can do that for algebraic transformations of varieties which are defined over any field. Okay, this makes sense. I mean, I have to compute this intersection in the algebraic closure of the field, but this makes sense. Okay, yes, that's a very good question. But let me finish with this thing. So this is a pure notion of algebraic geometry, except that I iterate, so there is some dynamics in it. I don't need to assume the map to be smooth. I don't need to assume that the projective variety is smooth either. I can do that for any rational transformation of any projective variety. Okay? And I get this type of dynamical degrees. So in fact, it does not depend on the choice of H. By this, I mean that if you change your embedding of X in another projective space, or in technical terms, you change the polarization, then the number you get at the end is exactly the same. It does not depend. Okay? It's also invariant under conjugacy. So for instance, if you have a birational map from variety Y to X, let's say the birational map is phi from Y to X, and you conjugate F by phi, you get a new birational transformation of Y, and the dynamical degrees are the same. Okay, so these types of numbers are invariant under conjugacy and do not depend on the choice of embeddings into projective space or polarization. Oh, yeah.
I'm trying to, can you compare this with the action of F on the p exterior power of X? Maybe that doesn't make sense.
What is the pth exterior power of a variety?
Well, I take the tangent, but
No, this we can discuss after, but no. I mean, there is some kind of lower bound. No. Well, by this, I mean it does not depend on the choice of the Kähler form. If you change the Kähler form on X, you get the same number. Okay, so the problem I want to look at, I mean, this sentence is not well phrased, but is the following. So I get numbers, which are these dynamical degrees, and I want to understand what type of numbers are these dynamical degrees, say for any projective variety. But what I will do is I will not look at projective varieties, I will look at the first interesting case, which is the case of surfaces. Okay, and I will do that for birational transformations. Okay. And if you want an analogy, there is a closely related, but in fact completely different question, which is pure topology. So you start with a homeomorphism of a closed surface of some genus G. So now S is a real surface, compact with no boundary, and you take a homeomorphism of it. You can compute a number, lambda of H, which is a dilatation factor of H acting on the fundamental group of the surface. Okay, so you get some kind of number which tells you how homotopy classes are expanded under the action of S. And you can also ask the same type of question, what type of numbers do you get, depending, for instance, on the genus of the surface? What happens when the genus goes to infinity, and so on, okay? So this is also a well-studied a subject, and if maybe you know about it. And what I am doing is something similar in the context of algebraic geometry. Okay, so what I want to do now is focus on the simplest case, which is non-trivial, which is the case of automorphisms. So regular diffeomorphisms, holomorphic diffeomorphisms of complex projective surfaces. So rational transformations, they may have indeterminacy points. I will come to that later. They are more difficult to study and more interesting. But for a few minutes, I want to focus on automorphisms to explain the relationship between this problem and Hodge index theorem. Okay. So I will use Hodge theory to say something about these dynamical degrees. And as we will see, the numbers that will show up are, in this context, are Salem numbers. Okay, so let me say that, so if you look at the definition of these dynamical degrees, now I'm focusing on surfaces. Okay, so you have, let's say, lambda 1, which concerns H11, and lambda 2, which concerns H22. So H22, in fact, is the top cohomology group. So the number you compute is just a topological degree of the map. So it's a number of pre-images of a general point. Okay, but here I'm looking at automorphisms, so invertible maps. So the top dynamical degree, lambda 2, is just equal to 1. The topological degree is 1. So the only one which is interesting is lambda 1. And so the definition, I mean, the formula is this one. Okay. So I want to explain some of the properties of these numbers. So for this, I will use a Hodge decomposition. So we have the second cohomology group over the complex numbers. It splits in 3 parts. So H20, H11, where you have Keller classes, and H02, which is a complex conjugate to H20. Okay, so the action of F on the cohomology preserves this decomposition. And in fact, on the H20 part, what you see, all the eigenvalues you see are just eigenvalues of modulus 1. The reason is the following. A class in H20 is represented by a holomorphic form, a globally defined holomorphic 2 form. Okay, and when you have a holomorphic 2 form, you can compute its volume. So if omega is a 2 form on X, you can integrate omega exterior omega bar on X and say that this is a norm square of omega. Okay, so this defines a Hermitian form on H20. And if you let your automorphism act on it, okay, you just pull back this, you pull back a volume form. So what this number is just the same number multiplied by the topological degree of F, which is 1. Okay, so this Hermitian product is invariant on H20, which implies that all eigenvalues you see on H20 have a modulus 1. And on H02, it's the same just by complex conjugacy. Okay, so this is why we can always restrict to H11, something that I'm in fact using since the beginning. Okay, and now on H11 there is this Hodge index theorem. First, there is an intersection form because you see it's a second cohomology group of complex surface. So as a real manifold, it's a 4-dimensional real manifold. So you have an intersection form. If you take 2 classes in H11, you can take their wedge product and integrate on X, and you get a number. That's the intersection form. And this intersection form is very special because its signature is, first, it's non-degenerate, and the second signature is 1 H11X minus 1. So H11X is just a dimension of this space. Okay, so there is something I'm doing and I didn't say. The Hodge decomposition works over the complex numbers. This is why I wrote it like that. Then I said that I can focus on the action on H11 of X with complex numbers, but also the complex conjugacy preserves this, so I can look at the real part, and I will focus on the real part. And this is this real vector space, which has signature plus, minus, 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 and so on for the intersection form. Okay, so it's a vector space with a quadratic form, which is of Minkowski type. Okay, 1 plus and the other signs are minus. Okay, so if you take an automorphism with an eigenvalue lambda 1 of F, which is larger than 1, then what happens is that there is an eigenvector which corresponds to this eigenvalue. And this eigenvector must be isotropic. By this I mean that the self-intersection here of the eigenvector is 0. So in my picture, this gray cone here is the isotropic cone for the intersection form. So this corresponds to vectors with self-intersection 0. Okay, and because the quadratic form, the intersection form is invariant, if a vector is multiplied by something which is greater than 1, it has to be isotropic. Okay. Then there is automatically, I mean, the determinant of such a map is plus or minus 1, so automatically there is also an eigenvector which is isotropic and which is divided by lambda 1. And then on the orthogonal complement of these two lines, you get something which is contained in the part of the space where the intersection form is negative definite. Okay, so here on this picture is invariant under my map. Here you have theta plus, theta minus. These two lines are isotropic, and the orthogonal complement here, the intersection form is negative definite. So in this invariant subspace, all the eigenvalues you see have modulus 1. So you have one eigenvalue larger than 1, one eigenvalue smaller than 1, and all the other one have modulus 1. Okay. But on the other hand, maybe I can come back. On the other hand, the eigenvalue, if I look at H2 of X with integer coefficients, all of them, they appear somewhere in this Hodge decomposition. Here, they have modulus 1. Here, they have modulus 1. Here, at most 1 has modulus larger than 1. And on the other hand, they correspond to eigenvalues of a transformation with integer coefficients when I look at the integral cohomology. Okay, so these eigenvalues are algebraic numbers. There is just one of them which is larger than 1, and the other ones are smaller than 1 or equal to 1 in modulus. Okay? Okay, so what you get is what we call a Salem number. Okay, so it's an algebraic integer, lambda. Lambda is larger than 1. You also have 1 over lambda among the Galois conjugates of lambda, and the other ones have modulus 1. Okay. So this is a type of numbers that you get when you look at automorphisms of algebraic surfaces. On the right, I also gave the definition of Piso number. A Piso number is an algebraic number, a real algebraic number larger than 1, such that all complex Galois conjugates of lambda are within the open unit disk. Okay, so in my definition, I put quadratic units, for instance, in the set of Piso numbers. So it depends on the authors, but for me, quadratic numbers are here. Okay. For Salem numbers, I explicitly impose that at least one of the conjugates is on the unit circle. So the smallest known Salem number is the so-called Lemmer number. So it's a 1.17628, etc. It's a root of a degree 10 equation, but it's the smallest known Salem number. We don't know whether there are smaller Salem numbers. Okay, so one conjecture is that the closure of the set of Salem numbers does not contain 1. Okay, so that there is a gap between 1 and the first Salem number. A stronger conjecture would be that the smallest one is the Lemmer number, but we don't know. And the smallest Piso number is known. Okay, it's called the plastic or Padovian number. It's the root of x cubed is equal to x plus 1. And the set of Piso number is closed, and it is contained in the closure of Salem numbers. Okay. So every Piso number can be approximated by Salem numbers. For instance, the golden mean is a Piso number. You can approximate the golden mean from below by Salem numbers and also from above. Okay.
So when estimate the number of Salem numbers, the ball of the height.
Oh, yeah, okay. So the Salem and Piso, for me, it's a real number here. The other ones are Galois conjugates of it. And so you can look at Salem or Piso numbers below some real number B. This number is typically infinite. Yeah. There are infinitely many Salem and Piso numbers below the golden mean, for instance. yes. I don't know how to answer precisely your question, but we can discuss this just after. Yes, you're right. Good. Okay. So why did I introduce these piezo numbers and these Salem numbers? Salem, it's clear. It's because these are the type of dynamical degree that we can see for automorphisms. And piezo numbers, now they will show up for birational transformations of surfaces. Okay, so let's move to birational transformations of surfaces. Okay, so the main difference between automorphisms, I mean, for this problem, between automorphisms and birational transformations, is that an automorphism acts on the cohomology and it gives you a matrix. And when you iterate the automorphism, you just have to iterate the matrix. For a birational transformation, it does not work like that. Starting with a birational transformation, you can define an action on the cohomology, but then if you start iterating the transformation, it's not the same as iterating the linear map. I mean, it doesn't work like that. So let me explain this phenomenon in the simplest case. Okay, so you take the case of the surface, which is P2. Okay. So the second cohomology group is just Z. It's generated by the class of a line in P2. So it's a one-dimensional space. Okay. Now, if you take a birational transformation of P2 and you use homogeneous coordinates, you can always write your transformations using homogeneous polynomials P, Q, and R of the variables x, y, z, with the property that they have the same degree and they have no common factor. Okay, and this common degree is the degree of f. And it's exactly the degree I was defining at the beginning of my talk. If you take a line in P2, say the equation of the line is ax plus by plus cz is 0, and you pull back the line, now the equation is what? It's ap plus bq plus cr equals 0. So it's an equation of a curve given by this p, q, and r, so it has degree of f. Okay, so this notion of degree is the same as the one I obtained by pulling back a line and intersecting with a line, which was my initial definition of degree. Okay, so this is the reason why we call these numbers dynamical degrees. So asking that the action on cohomology behaves well under iteration is like acting whether this notion of degree behaves well when I iterate. Okay? And it's the same as asking whether degrees of compositions are multiplicative. Okay. If I have an action, I mean, if it is a well-defined action of the group of birational transformation of the homology of P2, it should be a well-defined action on Z, and there is a problem. And here is an example. The degree is obviously submultiplicative, but when you compose two maps, so you write them with homogeneous polynomials, what may happen is that the composition has a common factor that you can factorize, and then the degree drops. So the only property you have that degree of f composed with G is less than degree of f times degree of G. And an obvious example is if you take the involution 1 over x, 1 over y, 1 over z. In homogeneous formulas, you just multiply everything by x, y, z, and you get P is y, z, Q is zx, R is xy. And if you compose f with f, I mean, from this definition, it's obvious. It's an involution, you get the identity. But if you compose this degree 2 polynomial formulas, it should be degree 4. It's because there is a common factor, which is x, y, z. And geometrically, this corresponds to the fact that each coordinate line is contracted by f onto a point, which is an indeterminacy point of f. So this type of cancellations. Okay. But in the first theorem in this subject is the fact that if you start with any projective surface and any birational transformation f of this surface, then you can find, you can make a birational change of variables. So you can do a modification of your surface just by blowing up points in your surface. You get a new surface y and a birational morphism from y to x, such that when you conjugate f with phi to get a birational transformation of y, the action on the cohomology behaves well. So the action of the nth iterate of f is the nth iterate of the action of f on cohomology. So you multiply matrices. And so lambda 1 of f becomes, in this case, it becomes the spectral radius of the action of this matrix on H11 of this new surface. If you need a large number of blow-up to construct Y, typically lambda 1 becomes an eigenvalue of a matrix on a very large vector space, and it becomes an algebraic number of very large degree. But in any case, lambda 1 of f with this construction becomes an algebraic integer, is an algebraic integer, and this is a typo. If it is, it's a typo. If it is larger than 1, then it has, so not equal to 1, not 11, okay, not equal to 1. It has to be a Salem number. This is what we observed for automorphism, or a Piso number, okay? And the property is that the intersection form is not invariant, but the cone of vectors with non-negative self-intersection is mapped into itself by the transformation. Okay, so you do not have invariance, but you have enough invariance in some sense, or you have the desired inequality to get the property that these numbers are Salem or Piso numbers. Okay, so that's the first result. It had been obtained by Jeff Diller and Charles Favre like 20 years ago. And excuse me? It depends on your best field. If you like algebraic geometry, you write the graph as a correspondence and you know it acts on cohomology or on the Néron-Severi group. Is it a good answer for you? Okay. Okay, so the first theorem we proved, in fact, so I stated as a theorem of like these 4 authors. In fact, in chronological order, it's Nagata first, and then Macmillan, and then what I did with Jérémy Blanc is the following. So, I will read the theorem in the chronological order. Okay, so you start with a birational transformation of a projective surface, and you assume that lambda 1 of f is a Salem number of, I insist here, I write of degree at least 2, I mean larger than 2, to mean that it's a Salem number, it's not a quadratic number. Okay? Then, so the first statement is due to Nagata and Macmillan. If f is an automorphism and not a birational transformation, then lambda 1 of f is larger than or equal to the Lemmer number. Okay, and it is, in fact, I mean, the Lemmer number is realized. So this part is due to Nagata and Macmillan. The first thing is that there are a lot of constraints on the type of maps that you get on cohomology when you restrict to automorphisms. Okay. This is linked to Coxeter groups and their Tits representation in a very explicit way. And this is the work of Nagata. And then Macmillan proved a general result, which is not directly related to algebraic geometry or dynamical degrees, which is look at certain Coxeter groups, look at elements in them and their Tits representation, and compute the eigenvalues. And you get some Salem numbers. And among these Salem numbers, what is the minimum? And he proved that the minimum is a Lemmer number in that case. And so to apply this part of the theory, what we had to prove is that it's some kind of rigidity result if you know that lambda 1 of f is a Salem number. In fact, this automatically implies that your birational transformation is conjugate to an automorphism. Okay, so just looking at this dynamical degree, some arithmetic property of the dynamical degree tells you that after changing the surface and making a conjugacy, your map becomes a regular automorphism. Okay. This theorem does not work for quadratic numbers. For instance, this map, x squared y, xy, so I'm writing in affine coordinates. The dynamical degree is a quadratic number, but this map is not conjugate to an automorphism. I mean, you cannot find a projective surface on which this map becomes regular automorphism. The same number appears for some automorphisms of a billion varieties. Okay.
How do you know that?
I know that because it's basic toric geometry, because this map that I just, so you can think about this map. You see, let's say x and y are in C star times C star. You think about it as a multiplicative group. And now this map is an automorphism in the sense of both algebraic geometry and group theory. And you can use a little bit of toric geometry to prove that. Okay, the fact that it cannot be compactified in a way which makes this map regular. That's one way to address this problem, which is good because it works in higher dimension. For this very specific map, it's easier to, I can explain using a Zariski resolution of indeterminacies. Okay, and now come to deeper statements, but that rely on the previous one. I look at the set of all possible dynamical degrees of all birational transformations of all projective surfaces. So I put all these numbers together. And now the statement is as follows. So this set is contained in, I mean, lambda 1 of f can be equal to 1. Okay. It's contained in the union of 1, the set of Salem numbers, and the set of Piso numbers. So the first statement is the consequence of the theorem of Diller and Favre from 2 slides ago. Okay? So this statement is just a Diller-Favre consequence. It is, this set is disjoint from the interval 1 and the Lehmann number if you remove 1 and Lehmann number. This is just a consequence of the previous theorem. Okay. So you have if you think that this set is the spectral shadow of all birational transformation, it's like a set of numbers in the real positive axis, then I'm talking about the dynamical spectrum of surfaces. And here you have some kind of spectral gap. Okay? So there is a gap between 1 and the Lehmann number. So this is just phrasing differently the previous theorem. The new result here is that this set is well ordered. So this means that you can have increasing sequences converging towards some limit, but if you consider a strictly decreasing sequence, it has to stop. Any strictly decreasing sequence in this set is finite. Okay. Which means that as soon as you have a number in your spectrum, there is a small interval above this number which without any spectral value, without any dynamical degree. So you have gaps everywhere. Okay. This set contains accumulation points, in fact, infinitely many accumulation points. As I said, it's easy to show that the golden mean is an accumulation point from below, but not from above because of the third statement. And this set is closed. Okay. And moreover, every Piso number that you see in this set is approximated by an increasing sequence of Salem numbers. Okay. So this is the algebraic structure of the set that I wanted to highlight. Okay. And as I explained at the beginning, it's related to questions in dynamical systems, for instance, to topological entropy. It's also related to questions regarding the structure of the group of birational transformation of a surface. So the most interesting case is the case of birational transformations of P2, the projective plane. So it's known as the Cremona group. It's an infinite dimensional group of birational transformations. And you can ask questions of group theory concerning this group. For instance, if you have look at the second statement, if you have two map G and F in this group of birational transformation of P2, and you know that F is conjugated to G, how do you find a transformation which does this conjugacy, which realizes this conjugacy? And the theorem tells you that to find such a map H that conjugates G to F, you only have to look among maps of degree which are explicitly bounded by this formula. So F and G are conjugate, this is what you know, okay? But maybe these maps are conjugate by something of very, very, very high degree, okay? In fact, no, the degree cannot be so high. I mean, the bound is extremely bad, but it's explicit. Okay, I think my time is over, so I have a next slide. So if you have questions, you can ask.
Questions?
Do you have a question? No, but the question was, what is the next slide? So maybe if you have a question first. Characterization, not that I know, okay? So the realization of Lemmer number has been done by Kurt McMullen on K3 surfaces and also on rational surfaces, which are the two places at which you can look for such examples. So the Lemmer number is realized in these two settings, K3 surfaces and rational surfaces. But otherwise, like a characterization, no. I don't know. Yes. No, nothing like that. No. I mean, maybe I have a way to phrase it differently. I mean, the exact question you asked, the answer is no, but maybe we can discuss this because maybe there is a way to change the question to get something. Oh, the problem here is so if you look at sequences of these numbers, I mean, converging to some point, I mean, an infinite sequence converging to a new point, the degree of these numbers as algebraic numbers have to explode, to go to infinity, which means that in this construction, in this theorem by Diller and Favre, to get a nice action on cohomology or Néron-Severi group in which you understand the matrices, you have to blow up more and more points. So in fact, what you are implicitly doing when you look at this type of questions is blowing up all points in P2, which in fact is how we do the proof. Okay, so we look at the injective limit of all possible cohomology groups when you do all these blow-ups. But then it's not finite dimensional vector spaces, but infinite dimensional hyperbolic geometries. So there was another question.
So do you know what ordinal the order type is?
Excuse me?
What ordinal the order type is?
Oh, the order type? Yeah, it's what's the notation? Omega to the omega. Yeah. I mean, it's not due to me, it's due to Anna Bott. But, can you say it again? Yeah, yes. Yeah. You mean the dynamical degree? The dynamical degree of this map? Yes, yes, it is also a limit. I mean, this type of dynamics is, as soon as you assume lambda 1 larger than 1, the dynamics is chaotic in some sense, has topological entropy, which is positive. That's the simplest example. You do not want to perturb this example to approximate it. It's a nicest example if you want to understand the dynamics.
I think the question was
But then I don't understand better the question.
There are some kind of okay, so the surfaces are fuzz, right? And of course you can consider.
Yeah, yes, you can do that. You can do that. I'm not sure. Okay. Okay. Okay, so I wanted to advertise some new results, okay, because this what I described today has I did this several years ago, and since then a lot have been done. So I just want to advertise 3 theorems and topics. All of them concern transformation in higher dimension, so not for surfaces. So the first phenomenon is that starting with dimension 3, there are birational transformations such that this lambda 1 is in fact a transcendental number. Okay, so there are examples for which these numbers are not algebraic. If you look at all possible varieties, all possible rational transformations, all possible fields of definition, the number, the set of dynamical degrees that you get is countable. So it's a countable set. But this countable set contains a transcendental number. So this is due to Jason Bell, Jeff Diller, Matthias Johnson, and Holly Krieger. They did an example in dimension 2 before that, but for a map which is not invertible, for rational transformation. The second topic that I would like to highlight is the fact that when you look at dynamical degrees, you look at the exponential growth rate of the sequence of degrees of the nth iterate. But maybe there are interesting phenomena when the sequence of degrees does not goes exponentially fast, but like a polynomial of the number of iterates, like n to some power. Or you can ask the question, if lambda 1 is equal to 1, so the exponential growth rate is, it's not exponential, is it automatically a polynomial behavior? So this we don't know for birational transformations in dimension more than 2, strictly more than 2. But for regular automorphisms, there are explicit bounds. For instance, this is a theorem by Dean, Lin, Ogiso, and Yang. If you have an automorphism of a complex projective variety X of dimension D, and you assume lambda 1 is 1, so all eigenvalues you see on H11 have modulus 1, then in fact, an iterate of the matrix is unipotent. So you have like Jordan blocks, and you can ask what is the typical size of these Jordan blocks. Or another way to phrase it, you look at the norm of the nth iterate on H11, how does it grow? A priori, it could grow like n to the dimension of H11. And dimension of H11 can be arbitrarily big, even if you fix the dimension of the variety. And the result is that it depends only on the dimension of the variety. It does not depend on the complexity of the homology. Okay, and this is an instance. What is behind that is really Hodge index theorem, but used in a clever way. Okay, that's the second topic, and the third one I wanted to highlight is a very recent result by Jun Xie, who is working in Beijing. I think he's famous now in Beijing. He proved something which is the following. You look at the Pth dynamical degree for a family of birational transformations. So now your birational transformation F depends on a parameter T. So in your polynomial formulas, you have a parameter in the coefficients. And when you vary the parameters, you vary the birational map. How does the dynamical degree vary? Okay, that's the question. And he proves a semi-continuity result. So it's upper semi-continuous in the Zariski topology. And it may look like a technical statement, but this is a crucial fact when you do dynamics or when you do what people call canonical height in arithmetic dynamics. And this works for all dimensions and all codimensions. So that's it.